Hey guys, I hope that y'all are doing well. This is a review video for the upcoming midterm exam number 2. And for this exam, I have chosen a previous year's exam along with a few multiple choice questions. And so we'll be going through all of them, and it will cover various concepts in stereochemistry, SN1, SN2, E1, E2 reactions. And before we dive into the questions, I just wanted to also note that from the feedback that we had gotten from our previous review session, some of you had expressed that y'all also wanted to have some content review. Unfortunately, because of the fact that we cover these exams, there are a lot of questions, and also in addition with the multiple choice questions, there can be a lot of time that is taken in this process. So in order to avoid the review videos from becoming very long, and to make it more concise, I have also added a link to a very helpful resource that I think will help all of you while you are preparing for your exams. It's actually a link to a website called Mastering Organic Chemistry. And in that website, they do an excellent job in covering a lot of the concepts that are covered in the introductory organic chemistry courses. So I hope that y'all can utilize that resource in your review, because I would highly recommend even just skimming over it to go over the basic concepts, so that when you actually get to the questions, you know what you're actually dealing with. So that being said, let's dive right in. So for the first question, we are asked to basically give, it's a nomenclature problem, where we are given a cyclopentane compound with a few substituents, and we are asked to give the IUPAC name and also indicate the stereochemistry. So, as is the case with nomenclature problems, let's first identify what our parent group is. So, because of the fact that we have this ring in the center where all these substituents are connected, we can say that our parent chain is cyclopentane. So now let's look at the substituents. Whenever we are trying to identify the substituents, the first thing we actually need to do is find out what the numbering in a ring actually is, because it's up to us, right? The choice, it's not as clear as, say, for example, an acyclic compound. So let's look at our substituents first. So when we see that there are 2 methyl groups attached to 1 carbon, and a cyclopropyl group and a methyl group. So let's write down what substituents we actually have. Right, so we have a cyclopropyl group, and we have 3 methyl groups. So the question is, if there are 2 groups on each of those 2 carbons, then we can't just choose our numbering in a way that makes it so that there are more groups with lower numbering, since there's 2 on each carbon. So the question then becomes, how do we decide which way to count? Do we start from 1, 2, 3, or do we start from here, 1, 2, 3? So in order to address this question, right, we need to consider the fact of the alphabetical order, right? So we see that for a cyclopropyl group, it starts with a C, and the methyl group starts with an M. So by alphabetical order, the cyclopropyl group would come first. So that's how we are going to do our numbering then. 1, 2, and 3. So with that in mind, we can already list out what our numbering for each of these is, right? So there would be 1, 3, 3, and 1 for cyclopropyl. But now the question indicates that we have to mention the stereochemistry, right? And whenever we're talking about stereochemistry, one of the first things that should come to your mind is the idea of a stereocenter. And a stereocenter is basically, or a chiral carbon, it's a carbon that has 4 different groups that are attached to it. And this allows for us to have 2 possible configurations, the R configuration and the S configuration. And to find out that, we need to look at the Kohn-Ingold prelog, or the otherwise abbreviated as the CIP rules of how to assign a configuration to a stereocenter. But even before we do that, we need to find out what our stereocenter is. So when we look at the compound, we see that for the carbons inside this ring, there is actually only one stereocenter, and it is the carbon at position 1, because it is attached to a cyclopropyl group, a methyl group, and this might be tricky, but you see that it's also attached to carbons on both sides of the ring that don't have the same sequence of carbons. So what I mean is, for example, above the stereocenter, you find that there are just 2 carbons, and each of those carbons are bonded to 2 hydrogens each. But below that stereocenter, we find that there's also 2 carbons, but the second carbon is attached to 2 methyl groups as compared to 2 hydrogen groups. 2 hydrogen atoms. So that tells us that these 2 sides of the ring are different. So we can, in fact, treat those 2 ends, or those 2 connections to the stereocenter, as different groups. So we can basically say that there are 4 different groups attached to that carbon atom. So that's what we'll be focusing on when we're trying to find out the stereochemistry. So when we look at that stereocenter and we see these 4 groups, now we can apply that CIP set of rules in order to find out its configuration. So let's go ahead and do that. There are 4 carbons attached to the stereocenter, right? So the first carbon, all of them at that point are equivalent, but in order to find out which is our highest priority group, we need to find out the one, or actually no, we can start, to make things easier, we can start from the lowest priority. So the lowest priority we would give it, so let me put the notation correctly. 1, 2, 3, and 4. So for 1 would have the substituent that has atoms that have the highest atomic number overall. And the lowest substituent, or 4, would have the atoms with the lowest atomic numbers. And since the 4 atoms immediately attached to the stereocenter are all carbons, that doesn't really help us. So we need to go one step further and see what atoms are attached to those carbons. So for an easy start, let's look at this let's look at the carbon for the methyl group. I've just added a dot to each of the carbons that we're now looking at. So when we look at this carbon, we find that the 3 other atoms that it's attached to besides the, we're not looking at the original stereocenter atom that it was connected to. We find that the 3 atoms are 3 hydrogen atoms. And when you look at the other 3 atoms that are attached to the stereocenter, we find that they're not all, that those atoms are actually not, the other 3 atoms that all of those other atoms are attached to are not only consisting of hydrogen atoms. So this means that this substituent has, in general, the lowest atomic number for its substituents. So that means that we would give it the lowest priority, or the lowest ranking, according to the CIP convention. Now that we've established what's our lowest priority group, our next priority is to see what other groups we can easily identify in our ranking of the substituents. So when we look at this, we find that for the 2 carbons within the cyclopentyl ring that are attached to the stereocenter, the other 3 atoms that those carbon atoms are attached to, besides the stereocenter, are, for the lower one, we find that it is C and the 2 hydrogens that are attached to it. So the carbon would be this carbon, right? That's the carbon that's attached directly to carbon number 2. And for this carbon, we find that it is also attached to another carbon and 2 hydrogens. So right now we can't see anything. We don't know what exactly these 2 are. But when we look at the carbon right here, right, the carbon that is attached to the group that is going out of the page, the cyclopentyl substituent, we find that that carbon is actually attached to 2 other carbons and a hydrogen atom. So this tells us something. The other 2 groups have only 1 carbon, right? In that, out of the 3 that we've chosen for each of these atoms, only this one has 2 carbon atoms that are attached to that atom. So that actually tells us that this is the highest in our priority, because even the methyl group and these two other groups, they don't have 2 other carbon atoms that they're attached to besides the stereocenter. So that immediately tells us actually that this cyclopentyl substituent is of the highest ranking. So I'm just going to abbreviate it as cyclopentyl. And with that established, now we can narrow our focus onto the 2 ends. Let me just clean this up a little bit. Okay. So now that we're looking at this end and this end, right, what we find is that we need to now extend our search to the next carbon, right? Because we got to a tie previously. We found that the 3 other atoms that those carbons were attached to besides the stereocenter were the same. So when we extend our search by 1 more atom, we see where things can start to change. So let me erase the previous annotations. When we look at these 2 carbons, the ones that I put the dots next to, now let's try to list out what 3 atoms that those carbons are attached to besides the previous carbon atom that was in the chain the previous carbon atoms that we looked at. So we find that for the carbon on the bottom, that it's attached to 2 carbons, and each of those carbons come from the attached methyl groups, along with 1 hydrogen. And for the dot at the top, the carbon corresponding to the dot at the top, we find that it's attached to just 1 carbon, right, the carbon below it, and 2 hydrogens. So now we see where things can start to diverge. We see that for the carbon at the bottom, there's 2 carbons here, but only 1 carbon at the top. So what this means is that the carbon that is attached to those 2 methyl groups has a higher priority than the carbon that it's directly attached to in the cyclopentyl ring. So I'm just going to mention that as the lower part of the ring, the lower carbon, and the higher carbon. So those are corresponding to right? So now that we've gotten our substituents nailed in our order decided, we can now actually look at how we can give the configuration for that stereocenter. So let me just go ahead and remove these annotations, and I can just put the numbering that we had found. So 1 for the cyclopentyl, 2 for the part of the ring that was attached to the lower carbon, 3 for the part of the ring that was attached to the higher carbon, and 4 for the methyl group. So when we look at this, we see that our lowest priority group is going into the page, right? The dash notation indicates that. So that actually makes our analysis a little simpler, because we don't have to imagine rotating this in our head. And that can be one of the challenging aspects of stereochemistry, especially when we're trying to find the configuration of a stereocenter. So let's try to find the direction in which the groups from 1 to 3 are going in order to evaluate their configuration. Since we see that actually that it's going in a clockwise orientation. So according to the CIP rules, we can assign this as a R configuration. So our configuration is R. So that gives us our final piece of information that we need in getting our name, getting the name of the compound. And again, to emphasize, the only reason we were able to just quickly get to that final value of that final configuration of R was because we were able to notice that our lowest priority group was going into the page. So that allowed us to make our analysis simpler. If it was, for example, coming out of the page, then we would have to actually flip the final configuration that we get to. But we'll see more examples of that later. So now it's time to write down our final name. When we do that, we see that we start off with the stereochemistry, so R, and looking at our substituents by alphabetical order, we see that cyclopropyl is the first substituent to be listed, along with its numbering. And now we mentioned the 3 methyl groups, so 1, 3, 3, trimethyl, I might run out of space, cyclopentane. The dash was just because I was running out of space. But that is what we get for our final answer. For question number 2, we are given a compound and we're also asked, just as in the previous question, to get the IUPAC name and also mention the stereochemistry. But in this case, we find that our stereochemistry is somewhat different. So we'll see that as we go along in this problem. So for this compound, we find that there are three double bonds that are in this compound, right? And when we're dealing with compounds that are not just completely saturated, that is, they only have single bonds, our way of finding out what the parent chain is slightly different. So in this case, we're actually trying to find the chain that has the most number of double bonds. So when we do that, when we try looking for such a group, what we find is that we can actually choose this as our parent chain. And what this would actually be, right, since now that we have our parent chain, we need to think about our numbering, right? So when we think of the numbering, the same rules apply as we had saw for, well, almost the same rules apply when we're trying to find out where we should start for our numbering. So whenever we are, so if we want to start from, like the question is, should we start from here, 1, 2, 3, 4, 5, or should we go the other way, right? But as we had seen in the previous part of the class, even in terms of nomenclature, we want to make sure that our numbering is low as possible. So it's better to start actually from the right end of the parent chain. So let me note down what our parent chain is. When we actually find the name, to get the name of this, we have two possible choices. The first way we can name our parent chain really, well, before that actually, we should recognize that there are two double bonds here, right? So this would give us a diene, or two double bonds within our main chain, within our parent chain. So the first thing that we have to realize is that it's a diene. But the second thing to realize is that it has 5 carbons, right? That main chain is composed of 5 carbons. So what this gives us is two possible ways of naming it. We can name, the first way we can name this is as penta 1,4-diene. And you might be wondering where the 1,4 comes from. The 1 comes from the fact that whenever we're trying to tell where our double bonds are located within the parent chain, we start from the first carbon of the double bond. So since we're going from right to left, right, so we have to start with the first carbon that we encounter when we go across that chain for each double bond. So for the first one, the first carbon atom of that double bond is at the carbon number 1, the position number 1. So that's where the 1 comes from. The 4 comes from the first carbon atom of the second double bond that we encounter when we go from right to left in our numbering. So that is just a short note, but an alternative way we can mention this is as 1,4-pentadiene. It's just a small change, but you can choose either or when you are writing down the name for this type of compound, the parent chain at least. So now that we've settled what the parent chain name is, we need to, as usual, look at the substituents. So the most conspicuous substituent, or the one that just pops out right in front of you, is the cyclohexyl group, right? So the cyclohexyl group is at the first carbon. The other substituent is the bromo substituent, or the bromine that is attached to carbon number 2. The next one actually is this ethynyl group. And if it was just a saturated group, so if it was an ethyl group, right? The reason why we say it's ethynyl is because there's a double bond there, just as a note. So let's also mention the numberings for each of these: 1, 2, and 5. So we have almost everything figured out for the name. The last piece in the puzzle is to figure out what the stereochemistry is. And in this case, we're not dealing with R or S, right? Because we don't have a stereocenter actually in this molecule. There are no stereocenters. What we do have, however, is a double bond that shows geometric isomerism. Sorry. So what this means is that, you know how we could either assign for alkene groups, we can give it a cis trans notation usually, but another way of mentioning the stereochemistry is also using something known as the EZ notation. And in this notation, what we're trying to do, we can assign a alkene group a stereochemical configuration of E or Z. And these come from German words, which I will not try to pronounce out of fear of butchering it. But I will, I just added there as reference. But what these two groups, or these two configurations mean, is that the highest priority substituent on either end of the double bond is either opposite from each other, so across the double bond, or they are on the same side of the double bond for Z. So the first thing we need to do is actually identify what is our highest priority. And in order to do this, we can actually use the CIP rules that we had touched on in the previous example. So let's see what our highest priority groups are with that in mind. So we see, let's start off with the right side. Our two substituents are the hydrogen atom and the cyclohexyl group, these two. So what this tells us is that we need to see which one of these two has a higher priority as per the CIP rules. And the CIP rules, according to the CIP rules, the cyclohexyl group would have a higher priority, right? Because the first atom that is attached to the double bonded carbon for the cyclohexyl group is a carbon atom, while the only atom that is attached for the other substituent on the right side of the double bond is a hydrogen. So when we compare a carbon versus a hydrogen, the carbon has a higher atomic number, right? So according to the CIP rules, this would give it a higher, it would give the cyclohexyl substituent a higher priority. So we can say that this is higher priority. I'm just going to mark it as H. So now that we've settled the right side, let's look at the left side. when we look at the left side of the molecule, we have two possible groups. Let me just erase some of the annotations because it's starting to block the view. So we have this branched alkene, and we have branched diene, and we have a bromo group as well. So again, which one has a higher priority? According to CIP rules, it would be the bromine, right? Because it has, the bromine atom has a higher atomic weight than a carbon atom, which is the first atom that is attached to the left end of the double bond for this branched diene. So with that in mind, we now see that our two primary groups on both ends of this double bond are actually on opposite sides of the double bond, so they're not on the same side, right? The bromo group is above the double bond, while the cyclopentyl group is below. If you kind of tilt the molecule, you can see that. So what this tells us right away is that our configuration is E for opposite. So now we have all the info that we need to go and start writing out our name. So let's, again, as in the previous example, let's start off by mentioning our stereochemistry. And now it's time to mention the substituents. And here we can use the same alphabetical order convention that we use whenever we're listing out substituents. So the bromo group comes first, followed by the cyclohexyl group, and lastly the ethanol group. So let's go ahead and mention that. 2 bromo, 1 cyclohexyl, apologize, I just caught a typo. What I meant to write a 3 here instead of a 5. My apologies. So this would be written out as 3 and then I've run out of space, so basically I'm just putting a little filler space in there. You could put either one of these two options in there, inside that little filler space that I mentioned after the dash. So this gives us our final answer. Before we dive into question 3, I just wanted to clarify some of the work that was done earlier. So for questions number 1 and 2, I just want to make a small note about the way I had written the stereochemical configuration. So actually, for this first, when we're mentioning the configuration, right, the R or the S configuration, it's usually also a convention to mention the number that is corresponding to that stereocenter, so along the parent chain. In this case, since the stereocenter was at the first carbon of that carbon chain, right, we could say that it is 1R, and then everything following that. But since it's the first one, we also have the option to just leave it as R. But if it was if the stereocenter was on another position, so if it was the second or the third carbon, right, that would then we would have to mention which carbon we were talking about. So we would say, for example, like 2R or 3R, so just as a note. And for, so that's just something to keep in mind. For question 3, we have this compound right here, and we want to write the Fissure projection of it. And our focus, right, the two stereocenters of this compound are 4 and 5, atoms 4 and 5. So it would be these two carbons that I've delineated with the two lines, right, 4 and 5. So I have, just to save some time, I wrote out the skeletal structure already, and I wrote down the Fissure projection almost, but I did not mention which of the two ends we have to, where the two substituents for each of these carbon atoms, how I would arrange them. I haven't put them yet because that ties into our discussion of determining the configuration. So, or writing out the Fissure projection in a way that gives us an S configuration at each one of those stereocenters. So let's start off with a at stereocenter corresponding to carbon 4. So that carbon is attached to an ethyl and a hydrogen substituent. So let's see if this matches with the name, right? The name tells us that we should have an S configuration at 4. So when we go ahead and use the CIP rules to give a priority to each one of these groups, we actually get the following. Get 4 at the hydrogen. We get a 1 for this part of the molecule, and sorry, I meant to include all of this, right? Everything that's to the right of the stereocenter. And we would also get, for this, we would get 2 at the left end of the molecule, or the left end of the stereocenters, so this part. And we would get an ethyl group as the third ranked compound. So let me explain. When we do this, we find that when we apply the CIP rules, we see that the hydrogen has the lowest priority, right? Because all the other atoms that are attached to the stereocenter are carbons, which have a higher atomic number. So therefore, the hydrogen would have the lowest priority. When we look at the right end of the molecule, so everything after the stereocenter, so that means this portion, right? We see that this carbon is attached, and that same carbon corresponds to this carbon. It's attached to a methyl group and a bromo group. So this is a big giveaway because there's a bromine attached to that carbon, and that tells us that all the other carbons that are attached to the stereocenter, so this carbon and the carbon that's part of the ethyl group, they're only attached to hydrogens and carbons besides the stereocenter. So this would give us the highest priority according to the CIP rules. And I had written a 2 for everything to the left of the stereocenter, so this part, by realizing that, okay, so we have a tie actually between the ethyl and this part when we just look at the first atom in that substituent, the immediate atom that is attached to the stereocenter. So we have to look a little bit more. We have to go one carbon further for each of these substituents. And what you find is that the second carbon for the left-hand side is attached to two bromo groups. And you can see that in the skeletal structure as well. In the ethyl group, there are no bromo groups, right? And there are no bromo groups attached to the second carbon of the ethyl group. It's only hydrogens. So that tells you right away that it's the second most, it's the carbon atom with the second highest priority. And that's how we get our order. Now, in order to find the configuration, we see that for a Fissure projection, these two groups, the ethyl group and the hydrogen, they actually are going out of the page, right? They're coming towards us. While, so we have to, like I had mentioned earlier, there are cases where the fourth, the substituent that's ranked as fourth or the lowest priority, according to the CIP rules, if it's coming towards you, if it's coming out of the page, then we have to flip the configuration that we initially find when we just try to evaluate the direction in which groups 1 to 3 are going. So let me explain. So when we go from our chosen priorities, right, we find that we're going from 1, 2, 3 in this direction. So we're going in a counterclockwise, in a clockwise direction. And you would think, oh, it's supposed to be R, right? But then again, remember, the H is coming, or the hydrogen is coming out of the page, right? It's in, it's not backwards. It's not it's not going into the page. So this means that we have to actually flip the apparent configuration that we found. So we found that it was R, right? But to account for the fact that that this H is actually coming out of the page, the correct configuration would actually be S, right? We would flip it. So that means that this tells us that our initial guess was correct. So we know that the first two groups are going to be the way we've ordered these two are correct. So that's the first thing that we had pieced out. The next thing that we need to consider is I'm just removing the numbering to make it a little easier. Okay. So now we need to figure out how we are going to organize the bromine and the methyl, right? So using the same CIP rules that we had shown earlier, you can apply the same principles. So I won't be, for the sake of time, I won't be repeating the same analysis, but you end up with this configuration as well. So this is our final Fissure projection, but there's also another alternative possibility. For Fissure projections, one of the rules is that if you rotate the entire molecule 180 degrees, right, you basically are having the same molecule. It doesn't change the molecule. You don't produce an enantiomer or anything like that. You just get the same exact molecule. So when we rotate it, we get the following configuration. It's really simple. So these are our two possible final answers. So for question B, we are given a set of different sorts of questions that ask us to rank things or to identify various parts in a reaction. So for part B, question number 1, we're asked to draw the lower energy transition state for this process. And the first thing that we need to consider is that in a reaction, there can be slow steps and there can be fast steps. And if you draw out a reaction coordinate or an energy diagram for a reaction, the slow step typically gives you the highest activation energy, and it might produce an intermediate, and then it might give you another step or another intermediate, and that is usually a smaller step, right? So the highest energy peak corresponds to the transition state for the slow step of a reaction, and the lower energy peak corresponds to the transition state for the fast step of the reaction. So let me just write that down. Highest activation energy, and this is often denoted by this sign E sub A. With this principle in mind, we can go forward in solving this problem. So we know that the transition state has to be since it's asking for the lower energy transition state, we're looking at the fast step. And so we're trying to find out the transition state that occurs when these two reactants combined. And what we can see right away when we look at the final product is that the bromine actually attacks the carbocation, the tertiary carbocation, and it forms a bromine atom. It forms a bromine substituent. So in this process, a pair of electrons, a lone pair, goes and forms a bond with the positively charged carbon. So when we're drawing the transition state, we can go ahead and write it like this. So now we have the Cr2, but it's forming a bond with the bromine, right? So the formation of a bond is usually just, or formation or cleavage of a bond is indicated with using dashed notation usually. So we include that bromine there. Now we're almost finished, but we also know that when we're drawing these transition structures, we have to include the partial charges. So which atom has a partial positive charge and which atom has a partial negative charge. So I'm just going to draw the box indicating the transition state, and there's the double dagger sign indicating the transition state. So in order to, since we know that the bromine is the negatively charged component that's reacting with the tertiary carbocation, we know that we have to basically put a, pen's been acting up. A partial negative sign and a partial positive sign at the carbon, since that was initially charged. So this gives us our lower energy transition state for this process. Question 2 asks us to place the following alkenes in order of increasing stability. So typically when we think of alkenes and their stability, our minds just immediately can go to, oh yeah, primary alkenes are usually less stable than secondary alkenes, which are less stable than tertiary alkenes, right? But this is a good example of where we need to be a little cautious when we are evaluating things like this. So I'll show you what I mean. So when we look at the compound to the left, we see that there is a double bond, and that the double bond is attached to 2 carbon atoms, right? So this means that the double bond is a secondary alkene. And if we look at the compound to the right, we see that there is a double bond, and that double bond is attached to 3 carbons, one here, and one here. So what this tells us is that there is, say, tertiary alkene. And when you look, when you look at the alkene here, what you see is that there are 4 carbons attached to it, right? So you would think that there's even more stability conferred to this molecule. But here's where the exception kicks in. So if we look at this very particular structure, we find that this is a bridged compound, right? It's a bridged bicyclic compound. And because of that, there is a rule called Brett's rule that comes into play. Brett's rule is a statement which tells you about where we can place a double bond in a bridged bicyclic compound. And it says that that these types of compounds cannot have a double bond at a bridgehead position, or basically one of these carbons, unless the rings contain at least 8 carbon atoms, right? And from looking at the structure, we know that there is definitely less than 8. It's a 6 carbon ring. And what this tells us is the Brett's rule applies here. So actually, having a double bond at this point is very energetically unfavorable according to Brett's rule. So I will also try to provide somewhat of a conceptual understanding of, or a conceptual explanation for this idea as well. So the reason why Brett's rule actually matters in terms of evaluating the stability is because this configuration is actually really energetically unfavorable. And the reason why that happens is that if you look at, since this is a pi bond, right? You have orbitals, you have pi bonding orbitals here and here. And these orbitals actually have, they're not exactly in the same orientation, they're not parallel to each other. So there is, whenever the orbitals are not exactly aligned with each other, it causes a lot of steric strain. And this can be have a high energy cost, and it can make the overall structure really unstable. So this is why Brett's rule kicks in and tells us that if we have a ring that's not large enough, right, to reduce the steric repulsion caused by this type of arrangement, we can caused this molecule to be very unstable. So actually, out of all of these compounds, right, this compound right here would be the least stable. But now that we've covered like the main exception to the trend we mentioned earlier about the stability of alkenes, when we look at these two, the double bonds are not at a bridgehead position, so they're not, they don't involve one of the bridgehead carbons. So we can apply our usual principle of stability for alkenes, right? So secondary alkenes are less stable than tertiary alkenes. So we have the following order. And this gives us our final answer for number 2. For number 3, we are asked to place these halides in order of increasing reactivity in an E1 process. So an E1 reaction actually highly favors it whenever you have a, in terms of the ordering of the E1 process. Actually, before I explain that, in an E1 process, the leaving group leaves, right? It, by its own, without any sort of other reagent involved, it leaves and it forms a carbocation. And the stability of that carbocation is what determines whether or not the reaction will proceed. If the carbocation is really unstable, that also equates to it being very energetically unfavorable. And in fact, when you look at an energy diagram, you see that the carbocation formation for both an SN1 and an E1 process, that's the slow step, or the rate limiting step. So we're going to try and see what types of carbocations are formed from each one of these, like whenever the leaving group, or the bromine group in this case, leaves, what carbocation is formed. So for this compound, we notice that if we, I'm just going to, instead of redrawing the whole structure, I'm just going to block out this part. We basically get a primary carbocation, right? We lose a bromine group, and now it's just a carbon atom attached to this ring and along with 2 other hydrogens, but it's missing a pair of electrons, so it's just a primary carbocation at this point. For the second one, when we block out this group as well, we see that we are left with something that's referred to as a vinyl, or let me just write it down, a vinyl carbocation. And because there is a double bond attached to the carbon that is positively charged. So the last one, when we remove the bromine group, we are left with a carbon that is just attached to 3 other carbons. So that gives us a tertiary carbocation. Let me just note this as well. So while it might seem, obvious that the tertiary carbocation is more stable, the one that we really need to consider is the vinyl carbocation, right? We need to see where it is in this hierarchy of stability. And actually, it turns out that vinyl carbocations are very, very unstable. In fact, they are more unstable than even just a methyl group that's a carbocation, right? And I'll actually write out this whole hierarchy. So basically, what I've written here is that this is the stability of various types of carbocations. But what we see is that let's start from the beginning, right? In the first one that has the lowest stability is the vinyl carbocation, right? Following that, we have a methyl group with a positive charge, right? And following that, we have a primary carbocation, and after that, a secondary, and then between the secondary and the tertiary, which is the highest stability, we actually have somewhat of a limbo. We have the allylic carbocation. So that means a positively charged carbon atom, and then just the carbon next to that, that carbon would be double bonded, right? And the reason why this is stable, particularly stable, is because this actually confers a thing called there's the possibility for resonance stabilization. So this double bond can shift here, and it can produce a new positive charge somewhere else. But the point is that the charge is delocalized, and that, as we've seen earlier from earlier content, resonance confers stability. And that's a big plus, especially when you look at a system like this, even a benzylic carbocation. So this this particular type of cation as well. The plus is for this carbon atom that's attached to this ring right here, a benzene ring. So that's also resonance stabilized because there's double bonds here that are willing to, that actually provide resonance stabilization. So this is just the hierarchy, but with this in mind, we can actually easily label the stability of these compounds, which corresponds to the reactivity in this E1 process. So since the vinyl carbocation is the least stable and therefore the least energetically the most energetically unfavorable carbocation, we find that it's the least reactive, right? It's the least likely to occur because there's the highest energy barrier that has to be crossed in order for this reaction to move on, in order for this carbocation to be formed and for the reaction to proceed. And following that, we have the primary carbocation. And lastly, we have the tertiary carbocation, since it is the most stable and therefore it has the lowest energy barrier. And since the height of the energy barrier, the amount of the energy barrier really tells you how much the reactivity of the reaction will be in a qualitative way. For question number 4, we're given a set of alkanes and we're asked to rank them in order of the increasing bond dissociation energy for a specified bond. So when we look at this, the bond dissociation energy is actually inversely related to the stability of the radical that's formed whenever you break this type of bond. And the radical would be formed in, say, something like in a radical halogenation reaction, or like radical bromination, for example. So let me just write that down. So with this principle in mind, we can go forward with this problem. So let's say that this bond underwent cleavage, right? And so then this proton goes off and as a radical with a radical, and it forms some other bond, but that's not our concern. So let's just block out everything here, and let's just put a a dot there indicating a radical. Sorry for the drawing. But when we see that, and this is corresponding to a single electron at that carbon, so what we have here is actually a primary radical. So that's our first observation. If we do the same thing for the second compound, where this bond is specified, what we do is we block this one out as well, and we just add a single dot there to indicate that it's a radical at that carbon. What we see is that this is actually a secondary radical because that carbon is attached to two carbons now. For the last compound on the right, when we remove this bond and place a dot there to indicate a radical, we see that this carbon, which has the single electron for the radical, is attached to three carbon atoms. And that gives us a tertiary radical. And what this tells us really is that, from what we already know, we know that primary radicals are less stable than secondary radicals, which are less stable than tertiary radicals. And from this principle here, what this tells us is that if the stability goes in this direction, right, then the bond dissociation energy has to go in the opposite direction since they're inversely related. So basically, this would have, the primary radical would have the lowest bond dissociation energy, followed by the secondary radical, and lastly, the primary radical. And this is our final answer for this question. For question 5, we are given a sets of different compounds, and we're asked to evaluate their stereochemical relationship, basically, whether they're enantiomers, diastereomers, structural isomers, or whether they're just the same compound. So let's go and try to evaluate this. When we look at this compound, this Fissure projection, we see that in both of these compounds, the starting and ending groups are the same. Where we differ, however, is in the positioning of these groups. So there are hydroxyl groups on the right for this molecule, but they're on the left on this molecule. And it's also flipped for the hydrogen atoms. So it turns out that these two are actually just identical. And the reason why is because there's a rule when dealing with Fissure projections, in that whenever you flip a Fissure projection 180 degrees and you get whatever that thing might be, the resultant Fissure projection, the resultant Fissure projection is the same as the original Fissure projection that you had before you rotated it. So what that means is that if you rotate this molecule, or this projection by 180 degrees, since these two are both ethyl groups, you're going to get the same, right? These two don't change, and that's what we see. But whenever it comes to the hydroxyl groups and the H groups, whenever you flip it 180 degrees, so if you were just, if you held this molecule in a hand, like if you actually, if you had a molecular model of this and you just flipped it 180 degrees, you would find that the hydroxyl groups actually end up on the other side, so on the left end. But basically, and the same goes for the hydrogen atoms. So this means that we have the same molecule. So let me just write this principle down. If you flip a Fissure projection by 180, and just to note, not across the plane of the molecule, but across the central axis that goes through the center of the molecule. So what I mean is, like, basically, if there was an axis going right through the middle of that molecule and you were to rotate around that axis, so if you were to rotate around that central axis, so this axis would be going out of the page, basically. It's hard for me to draw this in 3D, but basically this is not along the plane of the paper. That axis is not along the plane of the paper. It's perpendicular to the plane of the paper. So if you rotate across that axis 180 degrees, then you get the same compound. So we have evaluated our first stereochemical relationship. For the second pair of compounds that we're given, we are asked, when we look at it, it's not two stereocenters, but just one stereocenter. And when we see all the four groups and we see how they compare in each of these two compounds, it's not easy to tell exactly how they were rearranged. It's not like they were just rotated by 90 degrees or 180 degrees, because even the ordering has somewhat, even the relative orientation has changed. So let's assign the R and S configurations to each of these compounds and see how they stand up to each other. So when we do that, we have to first apply the CIP rules in order to assign the configuration. And when we do that, we see that the first one belongs to the hydroxyl group because it has an oxygen atom as its first, as the atom that's immediately attached to the stereocenter, and the other groups do not have oxygen atoms directly attached to the stereocenter. So that gives the hydroxyl group the highest priority. The hydrogen has the lowest atomic weight, so it is the lowest priority group. And now we have to evaluate the configuration for the aldehyde group and for the ethyl group. And right away, you can say that the aldehyde group has the second highest priority because this carbon is attached to an oxygen atom and a hydrogen atom. In the ethyl group, we see that this carbon atom is attached to two hydrogens and one carbon, and it's not attached to an oxygen group. So when we compare, my bad. Just a second. Sorry about that. What I was saying was, when we compare this carbon atom with this carbon atom, this one wins, and because it has a oxygen atom that's directly attached to it, while the other one does not. So that's why we give it a priority of 2. And the ethyl group would then correspondingly get a priority of 3. So we see that the way that these are arranged are in such a manner that it goes clockwise. And you might be tempted to just jump the gun and say that, oh, it must be the R configuration, but then you have to be careful because the fourth group, the lowest priority group, is actually projecting out of the page. So this means that we have to flip the initial the initial configuration that we had, right? We initially said it was R because it was going clockwise, but in order to account for the lowest priority group, which is projecting out of the page, we have to flip it to its actual orientation, which is S. And now that we have that settled, now let's look at the molecule to the right. So when we order it using the same principles as I had mentioned earlier, we get this. And if we find the arrangement, it's going counterclockwise. But again, to account for the fact that this H, according to the Fissure diagram or how it's arranged, it's actually coming out of the page. So we would have to do the same procedure. So our initial guess, or initial conclusion was the S configuration, but due to the projecting H group, we would get the R as our actual configuration. So we see that these two compounds, which have the same atoms, the same connectivity, but different orientation in space, these two have two different configurations, and that means that they are a set of enantiomers. Enantiomers always have their stereocenters flip or change their configuration, all of them. So that's a very that's a good way you can tell whether or not a pair of compounds are enantiomers, because each of their stereocenters basically changes their configuration. It's just a binary state, right? You could either be R or you could be S if you're a stereocenter. So now let's look at the third set of compounds. And now it's a little bit trickier because we have two stereocenters that we're looking at. So let's go ahead and do the same thing that we did earlier and assign priorities to each of these groups. So let's first look at the stereocenter at the top, the molecule. If we apply the same rules, what we find is that I assigned the 3 to specifically all of that. And it's for the same reasons that we've prioritized these. We've applied the same system of thinking the CIP rules in order to assign these priorities. And this gives us a clockwise orientation, but to account for the lowest group, the lowest priority group, which is the methyl group here, since it's projecting out the page, although we might have initially said it was an R configuration because we see the directions going clockwise, to account for that projecting methyl group, we have to flip it, so it would actually be S. And when we look at the top stereocenter for the compound on the right, we see something interesting. The methyl group and the hydroxyl group actually just flip places, right? So the methyl group goes to the left and the hydroxyl group goes to the right. And according to the rule of Fissure projections, when you interchange two groups in a stereocenter that are attached to a stereocenter while keeping the other ones fixed in their orientation, basically this causes the absolute configuration to flip. So if we had an S orientation here, this means that we will have an R orientation here. Now let's evaluate the bottom stereocenter in both of these compounds. So again, assigning priorities, we get the following. Let me just clean this up because it's a little messy. So we would assign the hydroxyl group as our highest priority group. Oh, sorry, it's erasing extra parts. Okay, so we would assign the hydroxyl group as our highest priority group. And then you might be tempted to just jump in and assign the aldehyde group as the next highest priority group, but you have to remember that this portion of the molecule, for this portion of the molecule, we have a carbon atom that is attached to 2 carbon atoms and 1 oxygen atom. And this aldehyde group, for this aldehyde group, this carbon is only attached to 1 oxygen atom and 1 hydrogen atom. So if we compare it, we're basically comparing so it's apparent that the large group is would get the next highest priority because there's 2 carbon atoms and no hydrogens. So that gives it an overall higher atomic number. So if we keep that in mind, we can say that, let me just erase extra. Give it a priority of 2, and then the aldehyde, and then the proton. And we see that it's the same configuration here. There's no difference in connectivity, and there's no change in the orientation of the groups either. So basically, we get, or actually first let me assign the correct configuration. So if we go from 1, 2, 3, we go in a counterclockwise direction, and to account for the projecting H atom, we see that we would actually finally get a configuration of R, right? You would think going to the left is S, but then to account for the hydrogen atom, we have to flip it, giving it a configuration of R. And since there's no change on the right, we get an R. So when we look at each of these 4 configurations on these stereocenters, we find something interesting. The stereocenter on the top changes its configuration as the hydroxyl and the methyl groups are flipped, but the stereocenter at the bottom doesn't change its configuration. And what this means is that this is not a pair of enantiomers, because as I had mentioned earlier, a pair of enantiomers always changes the configuration of all its stereoisomers. So this is a very important point to remember, especially when you go into the exam. Always make sure to see if all the stereoisomers configurations change. If not, you're dealing with a diastereomer. Diastereomers don't have the same requirement that all of their stereoisomers all their stereocenters have to change their configurations. Some may and some may not, but it does not matter. So with that, we've solved this problem. For number 6, it asks us to label this compound as either chiral or achiral. So when you look at it, it's very easy again to jump to a quick conclusion. Oh yeah, this is achiral because there's a plane of symmetry running. There's a plane of symmetry running right through the middle. But what you have to remember is that this molecule, if it was completely flat, you would be right if this molecule was completely flat. So none of the molecules were coming out of, none of the atoms were coming out of the plane of this molecule. But in fact, this molecule is not completely planar, because if we were to have atoms like iodine this close to each other, the steric repulsion is immense. The fact that they're so close to each other makes it highly unstable, and the molecule wants to be in the lowest possible energy state. And you'll see this theme over and over and over again in organic chemistry. So you might be asking then, what is the lowest possible energy configuration? Well, the key is to see that there is a sigma bond here. And what we know about sigma bonds is that they can easily allow for atoms to rotate, right? So there can be rotation here. And what this means is that if you think about it, the best way, what is the farthest distance we can isolate these two iodine atoms, for example? If we were to rotate the molecule along this sigma bond, well, it would be to make these two, okay, let me just erase it so it's a little bit more clear. It would be to make these two groups perpendicular to each other. So when we draw that out, how we would do that is we would write it like this. So from this drawing, what you can see, and I apologize, it's not the best, but basically you see that I've added wedge dash notation for the carbon-carbon bonds right here. So basically these two bonds, I've made one projecting out of the page and one projecting into the page, right? And this one is just along the plane of the paper. So basically these two rings are perpendicular to each other. So that would be the lowest possible energy configuration. So now that we have the geometry of the molecule settled, what we have to do is to see, well, is it chiral or achiral? So now we can't draw an apparent plane of symmetry, but what we can do is that we can draw its mirror image. So personally, the way I like to think of this is if you were, I know this sounds ridiculous, but if you were the molecule itself and you were staring at a mirror, right, how would you see yourself? I know it might be hard for some to visualize this, but basically, when you draw it out, right, so this would be the mirror reflection of that molecule. And with that, we have to see, well, are these two non-superimposable mirror images. So what that means is if I try to make this molecule in the same orientation as this molecule, are all the atoms going to be exactly where they were initially? So when this is very simple to see because when we actually try to orient this molecule when we try to rotate it along an axis that cuts right through the center of the sigma bond, right? If you try to rotate it 180 degrees, when you do that, what you find is that actually the positioning of the iodine groups flip. So when you draw out the final structure, you get when you rotate it, I'm not going to draw this half, but I'll draw this first part. When you rotate it the other way around, I mean, it doesn't matter if it's either way for a benzene ring because of resonance, but when you do this, you find that the iodine group is here and the bromine group is here, followed by everything afterwards. It's actually the same in this case for this part of the molecule. It doesn't change. They do superimpose, but the first part of the molecule, you see that the bromine is at the top of the molecule and the iodine is at the bottom of the molecule, or at least on the plane of the paper. And that's not the case for the original molecule, right? We see the iodine is at the top and the bromine is at the bottom. So what this tells us is that they are indeed non-superimposable mirror images. So this gives us a chiral molecule. For number 7, we are asked to place the letter of the reaction with the faster rate. And if the rate is same, write the same in the box. So let's evaluate these two reactions. The first thing we need to do, we can tell right away that these two are substitution reactions, right? This bromine is actually being replaced with an iodine group, right? So we can tell right away that this is a substitution reaction. So it's either SN1 or SN2. But the question is, which one is it? So let's look at our substrate, or the molecule or the alkyl halide that we're looking at. So we can tell right away that this is a primary alkyl halide. And as this is a primary alkyl halide, SN1 has a very strong preference for primary alkyl halides, and SN2 actually has a preference for the opposite order. So it would have a preference for tertiary alkyl halides. And the reason why primary alkyl halides are really involved in SN2 reactions as compared to SN1 reactions is because for SN2 reactions, they're preferred because there's less steric repulsion when the nucleophile tries to do a backside attack on a carbon atom. So we can rule out that this is really an SN2 reaction, sorry, SN1 reaction. And also, the question, when we look at these two reactions, we see that the nucleophile is iodide. And iodide is actually a weak base, but it's a good nucleophile. So these conditions are ideal for a SN2 reaction. The only difference between these two reactions, however, are their solvents. For water, we know that water is what? It's a polar, oh, sorry, my pen messed up, polar protic solvent, because of it has protons that can interact, the molecule itself is polar, and it has protons that can easily engage with the other compounds in the solution. And this is polar aprotic. Acetone is polar aprotic. When we draw out the acetone molecule, we get something like this. And we see that there are no protons that are willing to easily interact with the other compounds in the solution. So that's why we call it aprotic. And actually, for SN2 reactions prefer polar aprotic solvents. And the reason for that is that aprotic solvents, such as water, can interfere with the reaction. And you might be wondering why. Because the capability for water as a polar aprotic solvent to hydrogen bond can easily interfere with the nucleophile, or the ion in this case. And when it starts to interact with the ion is unable to react with the alkyl halide as much. So this actually affects the reaction rate. In polar aprotic solvent, the hydrogen atoms do not interact as much with the iodine nucleophile. So this actually allows for the reaction rate to go faster. And that is why we get B as our faster reaction. So now we reach the reactions part of the exam. And in this part, we're going to be evaluating various reactions given a certain substrate and a few reagents that react along with it. So let's dive in and let's see, for the first reaction, we have a compound that reacts with sodium cyanide in acetonitrile solvent. So let's try to break this down. So right away we see that it's not as simple as a simple alkyl bromide with just one bromide atom. There's 3 bromide atoms, right? So we have to see, we can't really ascertain from this structure exactly what type of reaction we're dealing with here. But we do know, when we look at the reagents, we see that we are given sodium cyanide, and the cyanide ion is actually a strong nucleophile, even though it's a weak base. And we're also given acetonitrile solution, which is polar protic. Since there are no protons that easily engage with the other compounds in the mixture via hydrogen bonding or through other means. So these are markers that tell us really that we're dealing with a SN2 reaction. Sorry. SN2 reaction. So now that we have that figured out, we can easily, decide which bromine goes and which one stays. So since this is a substitution reaction and specifically an SN2 reaction, we can go ahead and immediately see that this bromine doesn't work because it's attached to a carbon that is sp2 hybridized. And sp2 hybridized carbons cannot undergo SN2 reactions. And the reason for that is that a SN2 reaction, it's a concerted reaction, so it's all done in one step where the nucleophile, in this case the cyanide ion, would do a backside attack on the on an sp3 carbon and cause an inversion of stereochemistry. So all the compounds there, the stereochemistry changes. So the groups that were projecting out of the page all of a sudden now go into the page. So all of that stereochemical change also involves, it requires having a sp3 hybridized carbon. So right away we can see that this has to stay. Now what about this bromine atom? So we see that this bromine is actually attached to a carbon, a tertiary carbon. Oh, sorry, arrow went in the wrong direction. It's a tertiary carbon. And we know from SN2 reactions that SN2 reactions don't work well with, actually they pretty much don't occur with tertiary carbons because of steric repulsion. So that means that this bromine will not get booted through an SN2 reaction, so this too will stay. So that leaves us with this bromine atom to be removed. And it makes sense because this bromine is attached to a carbon that is a secondary carbon, and secondary carbons are involved in SN2 reactions. So with that in mind, when now it's time to actually, do the backside attack or to draw it out mechanistically to see how what products we would get. So when we do that, so this cyanide ion, I'm trying to draw it, will go and attack the carbon atom attached to the bromine, and this will cause the bromine group to leave, right? And not only that, but it causes the hydrogen attached to that carbon to invert its orientation. So instead of going out of the page, it goes into the page. And our final product is as follows. So let's look at this. When we see that the cyanide, group is actually projecting out of the page. So why is this the case? Well, whenever we attacked the bromine, right, it's called a backside attack for a reason, right? We don't attack it from the same side that a bromo group is actually in. So we wouldn't be attacking it from the back of the molecule, we would be attacking it from the front of the molecule. And so whenever it forms, whenever we actually, when the cyanide ion actually bonds with the carbon atom, it does it from the front of the molecule. And since there is an inversion of stereochemistry, the hydrogen atom goes to the back. It's pushed to the back, basically. And so that's how we end up with the final wedge dash notation that you see for that given stereocenter. So this is our final answer for number 1. For question number 2, we're given a Fissure projection of a molecule, and we're asked to evaluate the product after it reacts with the methoxide ion, or a methyl group attached to an oxygen, and overall that molecule is negatively charged, in a methanol solution. So we see that this methoxide group is actually a strong base. It's quite a strong base, because the corresponding conjugate acid, methanol, is a very, very weak acid, right? It's not, you don't really correspond it with an acid, methanol with an acid. So that means that once it's deprotonated, it's in an unstable state, and that's why it's a strong base. And because of that, we also know that when we're dealing with bases like this, it's a strong indicator that these types of bases will essentially interact with a proton in a acid-base reaction. Or in this case, that would basically result in an elimination. And since we're dealing with strong bases here, it's actually an E2 reaction. So when we look at this compound, looking at it as a Fissure projection can be somewhat of a pain. But if you, let's try to simplify things a little bit. So just to make our lives easier, we can denote the groups, the rings here, by the phenyl ring symbol. That's it's just a symbol for this type of ring. And you'll see it later on throughout the organic chemistry course series. So we can rewrite this Fissure projection like this. Sorry, my pen's still acting up. Okay, this is a bromine group. Okay, so we have this Fissure, this simplified Fissure projection, and one way we can look at this molecule is through the lens of a Newman projection, right? So we know that these groups are projecting out of the page, and that these are downward. These two phenyl groups are downward. So when we draw the Newman projection, we can draw it like this. And so these are corresponding to, if we were to look at this molecule in this direction, right, we would see that the phenyl group is pointed downwards with the hydrogen atom and the bromine atom pointing upwards. And we can do the same with this set right here, right? The hydrogen atom and the methyl group are pointed upwards as well, and the phenyl group is also pointed downwards. So this is a staggered Newman projection, or it's not exactly, it's somewhat tilted just to make the other groups visible. Now let's, since this is an E2 reaction, right? The thing about E2 reactions is that we want the proton being eliminated and the proton and the leaving group, the bromine, to be anti-periplanar to each other. So what does that word mean? It means that they have a dihedral angle of 180 degrees. So we can adjust this Newman projection, this Newman projection in such a way that we get the hydrogen atom and the bromine group to be anti-periplanar to each other. So if we do that, if we move the atoms in the back of the Newman projection, if we orient it by about 180 degrees or so, yeah, 180 degrees, we find that we get this type. This is the methyl group. And the phenyl group. So now it's in the prime state to undergo elimination, right? So we have, let's draw a little methoxide ion here. So this methoxide ion, with its lone pair of electrons, sees this hydrogen atom and it decides to take that proton. And in doing so, the pair of electrons that was connecting the molecule and the hydrogen, it migrates in such a way that it actually forms a double bond. So this goes into the space between these two ends of the molecule. So if I was to draw it here, basically it would go from, if I see the right end, yes, okay, it would attack that hydrogen and the electron would go into that original sigma bond between the two stereocenters. And ultimately, when you make a bond, you got to break a bond as well. And that causes this bromine group to be booted out. So we form an alkene. And we're not done yet. The stereochemistry of the final product matters as well. So let's look at how our remaining groups are, right? If we now have removed the proton and the bromine group, all we're left with is the, sorry, this is not supposed to be horizontal, it's supposed to be like this. It's supposed to be tilted. You find that the phenyl groups are anti to each other, or they're 180 degrees from each other, and the methyl group and the proton are 180 degrees from each other. So when we draw our final structure, those two sets of groups should be on opposite face or ends or faces of the alkene. So to demonstrate what I mean, I'll draw the final structure. So what we see here is that, as we see from the Newman projection, the methyl group and the H group are 180 degrees from each other. They have a dihedral angle of about 180 degrees. And the phenyl group, the same applies for the two phenyl groups. And this is what gives us our final answer for this problem. So make sure to always keep that in mind, especially when dealing with, when you start off with Fissure projections. You have to make sure that you can convert all of that given structure information into something that's a little bit more workable. For question number 3, we are given this compound, and it undergoes a reaction with NBS, or N-bromosuccinimide, and light. And what this reaction is essentially is a radical bromination reaction. So in a lab, when you would actually do this, you have a sample of NBS, but within that sample it also contains some of the bromine compound. So since bromine is diatomic, we also have some bromine in the solution. And this bromine is sufficient to kick off a radical bromination reaction, or initiate a bromination reaction. So basically, when you see NBS with light, you should be thinking radical bromination. The only difference, however, between just using normal bromine gas or bromine with light and using NBS with light is that you can think of NBS as just a more controlled way to do radical bromination. When you do normal radical bromination, the reaction can proceed in such a way that the bromine molecule, the diatomic molecule, is regenerated at a very fast pace. So it produces a very high concentration of the bromine molecule, diatomic molecule, and so this causes even for double bonds to undergo addition reactions, where ultimately what happens is that you lose the double bond, right? And we're not trying to lose the double bond here. We just want to make sure that we add a bromine in a certain location in the molecule without changing any of the double bonds or causing them to undergo addition reactions. So basically, in short, it allows for this, NBS allows for these types of reactions to happen with lower concentrations of bromine, so they're not going wild and out of control. So let's dive in. Now that we have a bromine atom, right? So let's say that we have a bromine radical, and this bromine radical, so after some of that bromine in the NBS sample interacts with light, producing the bromine radical. So let me just and now we have to think, where could this bromine radical interact with the molecule? And the first thing that should come to mind is actually this position right here for this carbon. And why, you might ask? Because whenever this bromine causes, it basically reacts with one of the protons, this bond cleaves in such a way that sorry, I should have, my arrow drawing notation is a little wrong. So one electron, so that's just signified by a single pronged arrow, goes along with the proton, while another electron stays with the carbon atom. And what this means is that we formed an allylic radical. And an allylic radical is simply a radical. I'm just going to erase what I've mentioned here so far. Okay. So allylic radicals are quite stable because of the fact that they are resonance stabilized. So this double bond here can actually do resonance with this radical, this carbon radical, because, for example, you can move this up here, messed up the arrows again. So you can move an electron here, and this radical can also move here, and also an electron can move here. So we can get another resonance structure, essentially, from doing this. And when we do that, so after it's reacted and it's produced its HBr, it's hydrobromic acid, now we have this resonance structure. And let's draw out that other resonance form, right? If we move all the electrons like I've drawn out with the arrows, we get another resonance form. We get something like this. And what this tells us is that there are two possible ways that a lonely bromine atom, that a radical that's seeking to interact with one of these two resonance structures, how the products will end up, right? And that's actually the termination step of a radical bromination reaction. When radicals start recombining to form stable products that don't then again react with other radicals. So if the bromine atom actually can, if it forms a bond at either one of these locations, or here, we get two final products. So for the first one, where the double bond was initially attached to in its initial position, we see that okay, let me redraw that because it's kind of bad. Okay. Okay. Where that radical was, we now have a bromine atom. And if you apply the same principle, So these are our two final products. For question number 4, we are given another compound, and it reacts with triethylamine. And triethylamine, as it turns out, is a bulky base, and a bulky strong base. Okay, bulky base, and it actually, since it is also a strong base, it wants to engage in an E2 reaction with this compound. And when we look at it, we see that there's a leaving group, it's a tosylate group, and we can label the carbon attached to this tosylate group as the alpha carbon, and all the other carbons that are attached to the alpha carbon can be labeled as beta carbons. So when we are dealing with E2 reactions, we have to remember that there is a particular rule in elimination reactions which is referred to as Zaitsev's rule. And Zaitsev's rule states that the base wants to basically remove the proton corresponding to the beta carbon that has the least number of hydrogens altogether. So what this means is that if we draw out all the hydrogens, so hydrogen here, 3 hydrogens attached to this carbon, and 1 hydrogen here, we find that this beta carbon has the least number of hydrogens, right? So according to Zaitsev's rule, you would think that you would have to basically remove this proton, causing there to be a movement of electrons to that sigma bond, forming a double bond, and also subsequently removing the leaving group. But this is just only one of 2 products. In fact, it is the minor product. And let's first draw out our minor product, right? When we do that, we get this as our final product. But again, it's the minor product, so okay. So you might be thinking, what's the major product then? And that's actually the Hoffman product. So the Hoffman product, you could think of it in a way as the opposite of Zaitsev's rule, the Zaitsev product, where basically instead of taking a proton from a beta carbon that has the least number of protons, we take a proton from the beta carbon that has the most number of protons. And in this case, that would actually be this methyl group right here. So what that means for us is that instead of attacking this proton, right, it actually, the triethylamine actually removes a proton from this methyl group. And that causes a migration of electrons from that original CH bond to the CC bond between that carbon and the alpha carbon. So it forms a new double bond. And it gives us the following final product. Gives us this as our final product. And I'll just add the carbons here to make it a little bit clearer. Right? We've lost a proton, but we still have the other two protons, and it's formed a double bond. So this is our major So again, just to recap, this is Zaitsev's. My pen is very unresponsive today, but to continue, this is Hoffman's product. So just keep these terms in mind, especially during the exam. For question 5, we're given the following substrate, and we're also we see that it undergoes a reaction with methanol, also with heat. So right away, heat should tell you that we are considering elimination reactions. But before we jump to conclusions, we also need to realize that there are 3 boxes, right? And also the thing is that there's a possibility for multiple products, and just because we see heat, it might be tempting to just jump right into an elimination reaction. But we also need to understand the nature of how these reactions work, and to have a good understanding of how these reactions work before we can come to these conclusions. And the thing is, with elimination reactions, we have to make sure that the elimination reactions are typically in competition with a substitution reaction, and that's the case for E1 reactions and SN1 reactions. For when we look at this substrate, we see that essentially there is a bromine attached to a tertiary carbon. And a tertiary carbon for a substitution reaction tells you something quickly right away. And that's that an SN1 reaction, substitution reaction, could occur. Because we have a tertiary bromide, right? That tells us, like, for SN2 reactions, this would not work because the fact that it's a tertiary carbon. So there's a lot of steric repulsion, and that can hinder such a reaction from occurring. So essentially what we end up with, especially in the presence of heat, we get a mixture of SN1 and E1 reactions. It's a combination, it's a competing combination of these reactions. And that's what gives us 3 possible products. So for both of these reactions, the first step that always occurs is the removal of the leaving group. So essentially this bromine group leaves. And what we're left with is essentially a tertiary carbocation. So this tertiary carbocation now is subject to two fates. The first fate is SN1, right? But it's not as simple as a lone pair on the methanol just attacking the positively charged carbon, because there is stereochemistry that gets involved, right? With SN2 reactions, what do we see? We see a backside attack. So there's an inversion of stereochemistry, right? Whatever groups were in a certain position, they get inverted. Like whenever you're outside and there's if there's a lot of wind and you're having, it's a commonly used analogy. If you're holding an umbrella and all of a sudden a gust of wind comes against you, right? Your umbrella basically inverts, right? It basically flips the other way around. That's the same thing, metaphorically speaking, that occurs during an SN2 reaction. Whenever a nucleophile attacks a carbon from the back side, as from the name, opposite to the leaving group, it causes all the other groups to invert their stereochemistry. Now, in the case of the SN1 reactions, there is also inversion, but there's also retention. So what I mean is that while you can always do a backside attack, you don't always have to. And the reason why is that there is a empty p orbital along on that carbon atom, and it can attack. So a methanol molecule can attack either end of that p orbital, right? It can go here, or it can go here. And so you're given two choices. And when you do that, right, if you're given those two choices, and they're both equally likely, you end up with what is known as a racemic mixture product. So you get two enantiomers because you are having two possible configurations of methanol in that molecule, and the methyl group that's already there also changes correspondingly. So you can, how do I put this? You can have the methyl group in its original projected state coming out of the page, or you can have it basically going into the page. So it all depends, right? So depending on which p orbital that you, which end of the lobe of the p orbital the methanol molecule attacks, you get two products, and this is after dehydration, so after the proton from the methanol is lost. So minus H. So just to show that after the proton leaves, you get two possible products. And actually, instead of drawing it here, I'll just so the first product involves and we have methanol or methoxide, I apologize, methoxide and the methyl group. So basically what we see here is this is the first variant of our product, right? But if it was to attack from the front end of the molecule, right, we would see something a little different. What we would see, in fact, is that sorry, just as a typo, there's a small error here. That CH3 group is not actually projecting out of the page. This is not projecting out of the page. It could be either or. It's actually just planar, so that's a correction. But again, if the methanol molecule were to attack from the backside, you would get this product. But if the methanol molecule were to attack from the front side, we would get just the same molecule, but the orientation or the stereochemistry changes different. It changes. So we are given the methoxide. Okay. And the methyl group. So these are our first two products. So now that we've figured out the substitution reactions, now let's look at the elimination or the E1 reaction. So since we have this tertiary carbocation, we return back to this tertiary carbocation. We see that there are three possible ways that it could potentially dehydrate, and the reason for there being three possible combinations is because of the fact that there are three beta carbons, right? So there are three different ways we can get the products for this reaction. So if we really look at this, if we try to do the dehydration for each of these, right, we could deprotonate this, we could deprotonate this, or we could deprotonate this, one of these three. And when we do that, a pair of electrons is from that original CH bond moves down, and it goes to the the carbon-carbon sigma bond, and it forms a pi bond. And this is true for all three cases. So what we get are actually a combination of three potential products. And actually, the major product would follow Zaitsev's rule, right? We would get the most substituted alkene, but there are two possible combinations for that actually. We could get either, if we were to address this beta carbon, right? If we were to focus the elimination reaction using that beta carbon, we get this as our final answer. This is our first answer. And just to right, that would be our first answer. But also we could attack this, and we would also get a alkene which is also a tertiary alkene. So this is another possibility. And this last option you see right here occurs when you do it at this beta carbon. So this would actually be the minor product because it's the least substituted. And since we're not dealing with a bulky base here, we don't have to worry about the whole anomaly of Hoffman and Hoffman products. So these two are a major compounds, right? Because they both have a tertiary substitution, and this just has a secondary substitution. So these are our final answers for question number 5. For question number 6, we are given this molecule, and it reacts with sodium amide, sodium amide. And I think you should know about sodium amide, and something that will actually serve you well, especially when you move on to Orgo 2, to know is that sodium amide is a strong base. A strong base. And it actually will engage in E2 bonding because of the fact that it's a strong base, and that there's a secondary alkyl chloride, right? So using that information, we can go ahead and find out what could be our possible answer. But there is a small problem, and that's that there's 2 chlorine groups, right? This is similar to a previous problem we had where we had multiple potential, how am I trying to say this? There are multiple halogens that can be removed, and we're trying to find the right one to remove. So let's try and figure that out. The first thing we can do, which can help us in understanding this, is we can draw a chair conformation. So I've drawn out the chair conformation just to save some time, and let's start examining it. So I've started it from this carbon here, and that's what you see here at the top. And when you look at this chair conformation, what do you remember about E2 reactions? E2 reactions require an anti-periplanar arrangement in order for them to actually occur. So that means that for the chlorine atoms, they have to be basically be anti towards the protons on the beta carbon. So again, let's draw out. So let's start off with this carbon right here. So this would correspond to this chlorine atom here. If we were to take a look at this chlorine atom, and if we tried, so there are 2 possible beta carbons, right? There's one here. Sorry. There's a beta carbon here, and there's a beta carbon there. So when we look at it, we see that there are 2 ways we can we can eliminate the proton for this specific chlorine atom, right? Well, we haven't looked at this one yet. And when you look at it, we can tell right away that it's not a good idea to deprotonate this proton, because this proton right here, because doing so would form a double bond that's actually that would be a secondary double bond. So that is, it would be attached to 2 carbons, right, on each end. It wouldn't be the most optimal case. However, if we were to eliminate this proton here and move the electrons down there to form a double bond, we see that such a situation would actually permit us to form a tertiary alkene. That is an alkene that has 3 carbon groups attached to it. So that means that basically it's better, so we should avoid deprotonating at this hydrogen. That's the main point that we get from doing this analysis, initial analysis. We shouldn't be removing these guys. But the question then remains, well, what about this proton and this proton here? Which one do we eliminate in order to produce the tertiary alkene that we're looking for? So this is where the subtleties kick in. Even though both these form stable tertiary alkenes, we have to think about the reaction from a microscopic level. So when we have this base, right, sodium amide wants to deprotonate, or it wants to remove a proton with the least steric repulsion, right? It doesn't want big bulky groups coming in the way and trying to block it from deprotonating a given proton. So when we look at this, right, if we had a sodium amide here, so I'm not going to include the sodium, but let's say that we had this sodium amide, it's negatively charged, and if it tries to remove this proton, it will encounter steric repulsion with this tert-butyl group, and that is unfavorable. But if we tried another situation where instead of trying to deprotonate here, there isn't the tert-butyl group is farther away, and the most repulsion we're really only dealing with is just this methyl group, but it's trivial compared to how much steric repulsion we would get when we're interacting with a tert-butyl group. So this is actually the ideal proton to deprotonate. And so when we do that, we actually get a double bond here, and we kick out this chlorine atom. And this ultimately gives us the following product. Right, we've basically removed that chlorine atom. So just to recap, we chose this proton in particular because it gives us a tertiary alkene, and that the way in which that occurs is done with the least amount of steric repulsion, since we're doing it far away from this tert-butyl group. And with that, we have answered this question. So now we've got into part D, and this part asks us to write down the mechanism for this reaction. And so when we go about doing this, just for the sake of time, I have written down all the steps, but I will go through all of them in detail, and this should give you an idea of how these types of problems should be addressed. So let's start off. So we have our substrate, and it reacts with methanol under heat to produce these two products to the right. So again, as we are dealing with substitution and elimination reactions, let's see what type of reaction we're dealing with exactly. So when we look at this, we see that we have methanol and we have heat. So these reagents, if y'all remember from a previous example, had hinted at the possibility of having SN1 plus E1 reactions. And for any real experiment, you'll see that these two reactions are actually competing. And especially, when you throw in heat, the differences are really amplified. So when you, since this is an SN1 plus E1 reaction combination, as I had mentioned earlier, these are basically two sides of the same coin. So what I mean by that is the first step for both of these reactions is always the removal of the leaving group. And in this case, that is the bromine, the bromo group. And so when it leaves, we form a secondary carbocation. Now, this carbocation can react as it is, or we can take advantage of the fact that there's a double bond that is nearby. And the reason why is because this is actually now an allylic cation. So there's a double bond nearby and resonance can occur. So if you were to move the electrons in that double bond around to the adjacent bond to the left, you delocalize the charge and you move it to the right. So we'll start off with that reaction. So what we see is that now that we have this positive charge here, right, we have it in such a way that we can go ahead and this methanol group, right, it will react with the carbon here, and it will form a new group that is positively charged at the oxygen. And this group actually is unstable because of the positive charge present, right? So in order to allow for the charge to become neutral, the proton has to be removed, this proton. And that can be done in two ways. So either we can use another molecule of methanol, or we can use one of the bromine anions that was generated in the beginning of this process. So once we do that, so I'll just, for example, if we were dealing with methanol, if a methanol molecule came by next to this proton, it would take this proton, right, and this lone pair, this set of electrons would go to the oxygen now. And the same scenario would happen if for the bromine anion as well. And ultimately, you're left with a methoxide group, and you're left with one of the products that was originally stated in the problem, right? And this is actually an ether as well. So that's the first thing, the first product. Now let's go back. Let's take a few steps back, and let's look at this resonance form. So at this point we have a positive charge at this carbon, right? And when you have a positive charge at a carbon next to a ring, there is always the possibility for a ring expansion. So what that means is that basically in order to reduce the charge on this carbon, right, the bond between these two carbon atoms can dissolve, and the electrons can essentially shift from there to here. And what that does is that it expands our 5 carbon ring into a 6 carbon ring. And ultimately, this causes the carbon that was originally the junction between the ring and the substituent to now lose 1 pair of electrons because of that shift. And now the positive charge is here. So because of that, now we have to address this positive charge. And that can be done by a methanol molecule interacting with that positive charge. And it produces this group, which now has a positive charge on the oxygen atom because of that additional bond with the ring. But we're not done yet. Just as in the previous case, we want to try to remove a proton. So in order to do that, we can there will either be a methanol molecule or a bromine anion that can deprotonate that proton, that substituent, and this ultimately gets us to our the other product that was asked of, right? So this is how we get to our 2 final answers. But I want to make a few remarks on this, in that resonance can play a very, very important role in reaction mechanisms, and you'll see this over and over and over again, especially for SN1, SN2, these types of elimination and substitution reactions, because often this involves the creation of charges that or carbocations, and if you have double bonds lying around nearby, there's always the possibility for resonance. And the thing is, these resonance structures are non-equivalent. Okay, the word non-equivalent for resonance structures means one thing, and that's if you have 2 equivalent resonance structures, if you do a reaction with each of them, so not the resonance structures reacting with each other, but if you took one of those resonance structures and you reacted it, you would get a certain product, and if you did it with the other one, you would get the same product, right? But with non-equivalent resonance structures, if you subject them to similar reactions, you can get different products. And that's actually what we see here. With a few differences, but what we see here is in the first step, methanol and methanol both interact with a positive charge, right? Later on, in order to remove the proton, either a methanol molecule or a bromine anion react with that proton to deprotonate, and we get our final products, which are different from each other, right? Visibly different. So what this tells us is that both of those resonance structures are non-equivalent. So my point here, my take-home point here is that whenever you're doing these types of reactions, always make sure to see if there's the possibility for non-equivalent resonance structures. For question number E, the last question on the test, we are asked to synthesize this molecule, and the starting reagents that we're permitted to have are cyclohexane, alkanes of 4 carbons or less, and any inorganic reagents. So let's look at our starting molecule, and let's try to identify what groups we have here. Right, we have cycloalkene, we have some branched, or actually, we have this group here as well. And overall, this is an ether, right? And typically, when you're given an ether, there's a high chance that it typically involves the formation. If we want to work backwards, right, retrosynthesis, a good starting spot is always here, right? Because from the problem statement, we're not given ethers, right? We're not given, or we're not even given alcohols or anything like that. So if there's a CO bond there, right, that means that it had to be formed from some sort of reaction. It wasn't a starting material. So we know that that's a very good spot to start our cleave the original molecule, like retrosynthetically. So when we do that, if we cleave it right there, the first possible way we can get to this final state is if we had this group here and this alcohol here, right? So what are we doing here, right? We're doing a essentially what we're doing is an SN1 reaction. So whenever you subject this type of halide with heat in the presence of an alcohol, what happens is that this leaving group essentially leaves by its own right the first step in an SN1 plus E1 reaction combination. And when this bromine group leaves, you're left with a positive charge here at that carbon. And the oxygen atom of this alcohol is capable of giving a lone pair, right, to that positively charged carbon. And after you dehydrate, and that occurs especially in the presence, like when you're in with heat, it leads to, deprotonate, it leads to the formation of an ether. And you'll see other forms of ether synthesis, especially next semester during Orgo 2, such as the Williamson ether synthesis. Just throwing it out there, just as a heads up. But for now, what we can work with is just heat, right? So this is a good way to combine like alcohols and alkyl halides, or especially not whenever we're dealing with like things like primary alkyl halides, but if we're dealing with secondary or tertiary, this is a permissible step. So so that's our first retrosynthetic step, so working backwards. So let's, part of it got removed. In the actual problem, you wouldn't draw these arrows or anything. I'm just only doing it for the sake of explanation. and you wouldn't include like all of these charges and everything. I'm just doing this to show this from a mechanistic viewpoint. So now that we have split our ether into two different compounds, we can basically trace out two paths to our original starting points, which include cyclohexane and perhaps an alkane. So let's start off with the cycloalkene, right? If we do that, let's first try to find a way to remove the bromine substituent. And I don't want to confuse y'all with this negative charge, sorry, the positive charge here. So let me try to, oh no, okay. Okay, so let me try to write over that with, well, I'll just write over, I'll just block it out so it's not going to confuse anyone. But our first task should be, because we're trying to get all the way back to cyclohexane, right? And cyclohexane obviously doesn't have any bromine substituents attached to it. So we want to try to remove that first. And this is usually just a rule, like we want to try to remove like the extraneous substituents like bromine or any halide or things like that before we really get down to removing the or changing the double bonds or triple bonds or anything like that, just as a general synthesis principle, like rule of thumb. So with that in mind, a good way we can do that is we can, not to remove it, but if we were to, so let's try to imagine what this would look like without the bromine, right? It would look like this. And if we wanted to get from here to here, a good step, right, as I mentioned earlier in a previous problem, is actually using NBS and light. And just to get back to this idea of why we use NBS, NBS allows us to do a radical bromination with low concentrations of bromine. So this prevents, the reaction from going crazy and even causing addition to the double bond. So basically causing the removal of the double bond. And that's not what we want. We want to do this in a controlled way. And again, we form a bromine at this position, right? Because when you have a hydrogen here, the two hydrogens that were here, the NBS, the bromine radical that is in that process, it basically causes the formation of a radical at this point, at this carbon, because electron is shuttled back to that original carbon. And now we have something special. We actually get, I'm just trying to remove these. We would actually get a allylic radical, because there's a double bond here, there's a radical here, and they're just one bond apart, right? So this easily allows for resonance stabilization. So that's why we would get a bromine specifically to one carbon away from the double bonded carbon if we used this NBS with light. And we would not have the issue of addition to having addition reactions with the double bond. So let me just remove some of the okay. So now we know why we're using NBS and light. Just so So just ignore this radical for now, or just ignore it. Again, only for demonstration purposes. You wouldn't show any of that in the actual synthesis. So now we have this cycloalkene. And the strange thing is we had removed a bromine earlier, but the thing is we can't easily just jump from a cycloalkane to a cycloalkene with our current given knowledge of how to do these reactions. So the best way to do that is through elimination, right? If you want to form a alkene from an alkane, we want to make that alkane into an alkyl halide. And we can, so the next best, I guess you can say the next best molecule that this can come from, this can originate from, is this alkyl bromide. And if we want to go from this alkyl bromide to this cyclohexene, we can do a E2 reaction, which can involve the use of tert butoxide or some other strong base. And now that we have this alkyl halide, all we need to do is find the reaction that allowed us to go from a cyclohexane to an alkyl halide. And this means that in this case, we end up having to use bromine with light. And you might be wondering, well, I had mentioned earlier that a bromine with light can cause these types of reactions to go crazy, but there is a way to work around that as well. If you have a given amount of, if you do a radical bromination reaction with a bromine and light, you can actually control this reaction from polybromination, or having way too much bromine, or like, you know, if you had like bromine here and a bromine here and a bromine, you know, just causing a lot of bromines to populate one given cyclohexane molecule. Instead of, to prevent that from happening, we can actually do, in synthesis, we can have a large concentration of cyclohexane, and this will actually reduce the amount of repeated brominations that occur. So if we have a lot of this initial product, it prevents, if we had a, okay, so let's think about the opposite case. If we had just a little bit of cyclohexane, right, and we had a lot more bromine, right, this means that there is so much room to do extra bromination on the few cyclohexane molecules there are. So you would get the major product for those types of reactions would be cyclohexane rings with 3 or 4 different, or even more, bromine atoms that are attached to it. But you can turn the situation on its head if you actually use a lot more cyclohexane than bromine. That's why we say excess cyclohexane. So this is how we get to our cyclohexane starting reagent. But now let's look at the other path, right? The path involving the alcohol. So clearly from the product, the question instructions, we're not allowed to start with an alcohol or anything with an OH group. So that means that we need to find a way to remove this OH group. Just as in the previous case, where one of the first things I did was I tried to find a way to, not to remove, better way to say it is, since we're doing retrosynthesis, we had to think about everything backwards. But the reaction that would allow for us to form a OH group, right, would have to involve some sort of substitution reaction with our current given knowledge of reactions. So that means that we can get to a compound with an OH group if we do some sort of substitution, and specifically a substitution involving an alkyl halide, and that's precisely the case. We can actually go from this alkyl halide to this group with a hydroxyl by using sodium hydroxide, because the hydroxide group, right, the nucleophile, can engage in a SN2 reaction because this is a primary carbon, and that allows us to get from this alkyl halide to that SN2 reaction allows us to get from this alkyl halide to this the compound with the OH group. So we worked backward one step. Now let's, but still, we don't have compounds that, for starting reagents, we don't have compounds that involve halogens. So we need to find a way to have a reaction that involves the formation of a compound of an alkyl halide, essentially. So just as in the previous case, we can actually use NBS and light. And why? Because we have this double bond here, right? This double bond needs to be preserved. We can't rely on something like bromination with radical bromination with just Br2 and light. No, we need to do something more controlled. So that's why we rely on NBS and light. And when we do that, we ultimately get the this alkene here. And still, we are only allowed to have alkanes. So we haven't got into where we want to exactly, but just as in the previous case, we can go from an alkane, pure alkane, to a alkene with the use of alkyl halide. So we can convert a alkane into an alkyl halide, which can then undergo an elimination reaction to form an alkene. And that's precisely the case. Here we see that sorry, I'm trying to get the right words for this. So we can do an E2 elimination with a compound like this, with an alkyl halide like this, which can cause this bromine to leave and form the alkene that we're looking for. And in order to do that E2 elimination, we can again use tert-butoxide or another strong base. So now we reached the last step of the retrosynthesis, which is how do we go from the alkane to the alkyl halide, right? So in order to do that, we can again rely on bromine and light, because there's no functional groups that are at risk with using Br2 and light. There's no double bonds that are at risk. So if we just use bromine and light on an excess amount of isobutane, we can get isobutane groups that have isobutane molecules that have a bromine group attached. So again, for the same reasons that I had mentioned for why we use excess cyclohexane, we can use excess isobutane as well to get monobrominated isobutane molecules. So that is how we get to the desired final products, where we have just a simple alkane, albeit branched, and a cyclohexane molecule. And with that, we have finished our retrosynthesis, and we have finished our exam. So thank you all for staying around for so long. The next part of the exam is actually, or not exam, the next part of our review will be on a few multiple choice questions that I have found from the ACS review guide for organic chemistry. So Now we're on to the multiple choice questions. And in this first problem, we are given 3 molecules and we're asked which of these molecules are Meso-Isomers. So Meso-Isomers, just as a recap, are stereoisomers that actually do not show chirality, even if they have a few stereocenters or chiral carbons. So with that in mind, let's try looking at each one of these molecules and assessing whether or not they are Meso-Isomers. For the first compound, we have a cyclopropane ring, and one of the carbons has 2 Cl atoms attached, 2 chlorine atoms attached to it. We can tell right away that it's not a stereocenter because it has 2 identical groups, which are in this case the chlorine atoms. And the same principle applies to the 2 other carbon atoms on the cyclopropane ring because there are 2 hydrogens for those. And so what that means is there are no stereocenters for compound 1. So the issue of whether or not it's a Meso-Isomer is not even relevant. It doesn't apply. So we don't look at this compound. So options A and D are out. Now the question is 2 or 3 a Meso-Isomer? So we know one of them isn't. So when we look at the second choice, we find that there are 2 stereoisomers, one here and one here. And the question is, well, now we know that it has stereoisomers, but is the molecule chiral? And if you look at the molecule, you realize that there can be a mirror plane that can be drawn right through the center of the cyclopropane triangle. This is a bad drawing. Let me do this again. So a mirror plane can be drawn right, still messed up, right through the middle. And we see that if you look at on both sides of this mirror plane, I've only just drawn it as a line to make the drawings a little bit more understandable or visible. So we see that on both ends of this mirror plane, the molecule is symmetric. So this immediately tells us that this molecule is achiral, and therefore the Meso-Isomer, even if it has 2 stereocenters, the molecule is still achiral, which makes it a Meso-Isomer. So B would be our final answer. But let's just take a quick look at option 3, just to be thorough. So whenever we look at these, we find that there are again 2 stereocenters. And if you actually assign RS notation to these 2 stereocenters, what you end up getting are R and R. So the interesting thing about it is that when you do a mirror image reflection, you will get a compound that actually has the stereocenters will have S configurations. So that means that these 2 are enantiomers. These 2, this and its mirror image, are enantiomers. So basically the molecule has chirality, and it's definitely not a Meso-Isomer. So it's just an exercise that y'all can try. But when you're on a exam, for the purposes of time, you can just go ahead and choose B as your final answer and be done with it to save time. For this problem, we're given 4 Fissure projections, and we're asked to evaluate a few statements about them and see whether or not they're true, and choose the statement that is correct. So for choice A, we are given, it tells us that projections 1 and 3 are enantiomers of each other. So what this means is whenever we take the mirror image of 1, we should be able to get a non-superimposable mirror image. But the thing is that to save time, we can first quickly realize that actually 1 and 3 are just identical compounds. And so let me explain. If you take Fissure projection 1 and you rotate it by 180 degrees across the axis that is perpendicular to the plane of the paper and exactly at the center of the Fissure projection, if you rotate it 180 degrees, what you'll find is you can go from 1 to 3, and if you do another 180 degree rotation, you can go back to 1. So this tells us something very important. It tells us that these two compounds are identical. So if they're identical, that means they can't be enantiomers. So this means that A is not a correct answer choice. When we look at the statement for choice B, it says that 2 and 4 are identical. But again, this statement would be incorrect as well, because if we rotate this molecule by 180 degrees, we don't end up with 4. In fact, 180 degrees, we actually end up with the same exact molecule. And that's an exercise that you guys can do very quickly. But you would end up with the same molecule, and you would not end up with 4. And so that means that 2 and 4 are not identical. So for this question, we have already come to the conclusion that question choices A and B are incorrect answers. And I just erased the previous annotations just to make our work easier. So now the question is C or D. And let's look at choice C first. At choice C, we find that it says that 2 is a Meso-Isomer. But we find that this choice is also incorrect. Because if you were to assign absolute stereochemical configurations to each one of these stereocenters, what you would get is R at the top and R at the bottom. And another thing, and the thing is that with Meso-Isomers, they have stereocenters that are opposite of each other. So R and R are not, they would not fit under that category, that definition. And in addition, there is no mirror plane of symmetry that runs down this molecule either. And in meso compounds, there's always a mirror plane of symmetry between the two opposing R and S configurations for the stereocenters, but even that is not present. So we can rule out C as an answer. However, for question D, we come to find that this is the answer, not only by elimination, but if we take a look at it and we try to evaluate it, we can see this is the case as well. So for the first case, the first stereocenter, what we find is that it's basically the same configuration of atoms as was for this stereocenter, right? So these two are identical. This and this have the same configuration, same orientation of atoms. So we know that this must also be R. However, for the bottom stereocenter, we find that these two groups, the hydrogen atom and the hydroxyl group, they actually switch positions. And according to the rules for Fissure projections, we know that when you interchange two groups in a stereocenter and keep everything else in the same orientation, that causes the orientation to flip. So that gives us an S configuration. And if you work those out individually, you find that this is the case. So this is a strong indicator these two are indeed diastereomers, because enantiomers, for enantiomers, the stereocenters, all of the stereocenters, they change their signs. They flip, right? So if you had an R in one, it should be an S in the other. But we find that this is not the case here. Even though the bottom stereocenter does flip because we interchanged the two groups, the top two stereocenters actually have the same configuration. So that means that these two are not enantiomers. They are in fact diastereomers. So that is how we end up with D as our final result. So now let's move on to the next question. So it asks us, what is the stereochemical classification of 1s, 2s, 1,2-cyclohexane diol and 1r, 2s, 1,2-cyclohexane diol? And this actually puts the principles that we had just discussed into play. So when we look at this molecule, we don't even need to draw it out. The focus for stereochemical classification are the stereocenters, so the first carbon and the second carbon. And what we're looking at specifically in order to solve this problem are their configurations. So we find for the first compound, we find that the configuration is S. However, for the corresponding one, it's an R, so we notice there's a flip. And so that's our observation for the first stereocenter. For the second stereocenter, we find that the configurations are the same. There's an S here, and there's also an S here. So, based on our previous discussion, we know that this can't be a pair of enantiomers, because in a pair of enantiomers, there's always going to be a flip or a change in the orientation for all of the stereocenters. So if these two were enantiomers, what it should really say here is 1R, 2R. That's what it should say if there were two, if it was a pair of enantiomers. But however, since the S configuration stays the same for both on the second stereocenter, we know that this means that it could only mean really one thing, which is that these two are indeed diastereomers. For this question, it asks us which bromine would react the fastest in the SN2 reaction shown below. And that means that we have to understand what factors favor and disfavor an SN2 reaction. And this is a topic that we had actually touched on earlier when we were evaluating several problems. So the first thing we need to realize is that when we look at each one of these potential alkyl bromides, we need to classify what they are. So for choice A, we find that we actually have a secondary alkyl bromide, because that bromide is attached to a carbon, which is also attached to two carbons, so that makes it a secondary alkyl bromide. For choice B, we find that we actually have a primary alkyl halide, because the bromide is attached to a primary carbon. For choice C, we find that the bromine is actually a vinyl, that compound is a vinyl bromide, because that bromine is attached to a carbon that is double bonded to another carbon. So that bromine isn't even attached to an sp3 hybridized carbon. So let me just note it down. Vinyl. And the last one is actually a primary allyl bromide. Alkyl bromide. And the reason for that is that there is that carbon that the bromine is attached to, right? This carbon is adjacent to a carbon that is double bonded. There's a double bond here. So that means that we know that this bromine is indeed, we're dealing with an allylic compound here, an allyl bromide. So from our understanding of SN2 reactions, we know that SN2 reactions, firstly, they only work with with alkyl halides that have carbons that are all sp3 hybridized. So that immediately rules out C. And now we're left with A, B, and D. Choice A can also be ruled out because we know in terms of reactivity that SN2 reactions are faster when they're dealing with primary alkyl halides as compared to secondary halides. Secondary alkyl halides. So now we're left with B and D. And it turns out that whenever you have whenever it's allylic, whenever this primary alkyl halide is actually allylic, it actually speeds up the reaction a little bit more. And this is due to a phenomenon called hyperconjugation. So if we were to draw out the structure of this reaction, or so let me just apologize, that's dash notation here. And there's the cyanide nucleophile. So when it does its backside attack, we get into a very interesting transition state. So what we find is that, so we're right in between this SN2 reaction, this process. Again, it's a one-step concerted reaction. So a cyanide ion is being formed is forming a bond with the carbon at the same time as the carbon-bromine bond is being dissolved. And the thing about allyl bromides that make them special compared to just pure primary bromides is that there is this idea of hyperconjugation. So basically, this is the double bond, right? The double bond that we had seen earlier from the formula. And this double bond actually plays a role in the transition state. See, these p orbitals actually interact with the orbitals of the bromine and the cyanide ion during this transition state, and it actually causes a sharing of electron density. And this sharing of electron density leads to stabilization, and this actually lowers the energy of the transition state, making it more, giving it a higher reaction rate, like from a thermodynamics standpoint. So this is what allows for an allylic primary allyl bromide to have a higher reaction rate as compared to just a plain primary bromide. So I just want to give some of the concept, the theory behind that, but this is why we would end up with D as our final answer. So for this question, we are given this alkane, and we are asked, or not really alkane, just a compound, we're asked what is the major product of this reaction. So we see that it reacts with potassium hydroxide in ethanol solution, and we're trying to find out what product results from this. So right away, what you can notice is that this is actually written in bond line notation. So bond line notation is actually really helpful, and one reason it can be helpful is that it can easily be translated into a Newman projection. So if you were to look at this molecule from this direction, right, if we were to look this way, right down through that middle bond, that middle sigma bond, we can draw a Newman projection like this. By the way, the C6H5 groups are the phenyl rings, or the ones that look like benzene. Right, I'm just looking down through the middle, through that single sigma bond in the middle. And we would get this as our Newman projection. And the reason why I drew this Newman projection is because if you look at the reagents, we have potassium hydroxide. And potassium hydroxide is a very strong base. And so what this tells us is that there is indeed the possibility of an E2 reaction. And if we're dealing with an E2 reaction, then we have to make sure that our leaving group, or the bromine here, is in an anti-periplanar position to the proton that is going to be kicked out as well. And in this case, it's this proton. But from this Newman projection, we see that they're not in an anti-periplanar position. They're about 60 degrees away from each other, or so. So what this means is that we have to rotate this molecule. And if we rotate it, what we find, if we try to make it so that these two groups are anti to each other, we get the following configuration. So now we find that these two groups are anti to each other. So what this means is that now we're in a prime position to do an E2 reaction. So the hydroxyl anion from the potassium hydroxide swoops in and it deprotonates. And this causes the electrons, that original CH bond, to move down and go into this double bond. So if you were to look at the bond line notation, that would mean that the OH group deprotonates right here, and it pushes these electrons into this sigma bond. And the last step of that would be that this bromine gets booted out. And what we find is that these two groups go away. So now let's look at the remaining groups, right? We find that a methyl group is anti to another methyl group across the double bond, the newly formed double bond, and a phenyl group is also anti to another phenyl group that is across the double bond. So that tells us something. It tells us that C is our final answer, because that is what matches the descriptions that we have so far. We find that the phenyl groups are anti to each other, and the methyl groups are anti to each other. And that is how we end up with C as our final answer for this question. And now we've reached our last question of this multiple choice section. So we are given this interesting compound, a cyclobutane ring with a few substituents, and we're asked to find the final product. And we're given hydrobromic acid as a reagent. So let's go ahead and try to solve for it. So we're given our original reagent. And now we add HBr. The thing is that HBr is a strong acid, and it wants to engage in an acid-base reaction, right? So the OH of this compound can donate a pair of electrons to this HBr, and that causes the formation of a water molecule being bonded to this compound. And the oxygen atom of that water molecule is positively charged as a result. And we also have the bromine anion, which will come into play later. So now we can see, since we have this water molecule likes to be by itself. It doesn't like being bound to the structure, and it would prefer to be by itself because water is a stable compound. Otherwise, no life would exist, right? So it would rather be on its own. So this pair of electrons goes to this OH2, and what we're left with is this compound. A secondary carbocation. Now this looks very familiar, doesn't it? We have a ring, and it's attached to a carbon that is positively charged. And when you see this type of situation, one of the possibilities that should immediately pop up into your head is ring expansion. So, and that turns out to be the case. turns out that this bond ends up moving to here, right? So this carbon atom forms a bond with this carbon atom instead of this. And we get the following compound. And the reason why we have that plus sign is because this carbon corresponds to this carbon. So whenever it lost its original bond, it did not have a fulfilled octet, so that's why it has a positive charge. And now here's where the bromine comes into play. So this bromine is negatively charged, and it's looking for a positive charge that it can interact with. And now we have that positive charge in an ideal position. So this negative charge sees this positive charge and it reacts with it. And what we're left with is C as our final answer. And with that, we have concluded our review session. I hope that you guys found this to be helpful. Best of luck with your exam. Please feel free to contact me or Danny in these upcoming days as y'all prepare for your exam. But again, best of luck.